Right. I think the time is 2:05, so it's about time to start. Welcome, everybody. So we continue with looking at stochastic processes. Okay, so we've introduced the idea of having a time into our probabilistic discussions yesterday. So now we have a filtered probability space, so omega f, and then I have a sequence of sigma algebras, that's an increasing sequence, and a probability measure. So this is filtration, and that means that Fn is included in Fn plus 1. And our interpretation is that Fn is the information that we have at time n. We talked about the process x is adapted if xn is Fn measurable. That means that my information at time n allows me to understand the value of my process at times n. And then we talked about stopping times. So tau was a stopping time. And the idea was that this was a way to encode times which are not boring deterministic, which could be random, but which are of this type which they do not require us to foresee the future. We know when they happen. Right? An example was the first hitting time. So an idea, an example to have in mind is we had our simple symmetric random walk, so something that goes up and down, and then maybe we looked at the first time it hits level 4 and level -2. And so this was tau. Tau was the first time that my simple symmetric random walk, Sn, goes out of -2 and 4. It's just a way of writing it hits -2 or 4. And we also understood that we can introduce f tau, the information known at time tau. Okay? So here, clearly, we expect that this will happen reasonably soon, but there are some paths which will keep going up and down, up and down, up and down for a very long time. So there's no upper bound on tau. I cannot say tau is less than 100 almost surely. So there's no ordering that will tell me that f tau is included in f100. Okay? Nevertheless, I made sense of this sigma algebra of what's known at time tau, and in particular, we saw that S tau is f tau measurable. So event which says S tau is equal to 4 is also f tau measurable in particular. Okay? Which is natural. When this happens, we know whether we exited the band here or here. Right? But we don't know in advance what will happen. So today we introduce martingales. So PMM, we started quite quickly with probability and measure. It took us quite a long time to introduce martingales, but here we are finally. So definition. So a filtered probability space is fixed, and it's always relative to this probability space that I introduced my notions. So an integrable, or a stochastic process, let's say, x, so this is xn, is a martingale if three things happen. One, x is adapted. Two, xn is integrable, so expectation of xn is finite for all n's. And these are sort of your baseline conditions, okay? They're almost always satisfied, but that doesn't mean that in an exam you don't have to verify them, okay? So there's still important things to verify. And then the last condition is the one that really is the key, which says that expectation of xn plus 1 given fn is equal to xn almost surely for any n greater or equal than 0. And with our understanding of conditional expectation, what I'm saying is that whatever happened so far, if I know where I am, and I'm trying to somehow best predict my position one step ahead, giving the history of what has happened, then my prediction will be my current value. Now this language of predictions was coming from L2, so I needed square integrability, but the conditional expectation was something that we defined for integrable random variables, so this makes sense. So your process can also be a sub-martingale or a super-martingale. These two conditions stay the same. And so this is somehow a mathematical model for a fair game. Okay, we're playing a game and maybe I'm winning or you're winning. But at any point in time, my expectation of my capital, let's say, or my winnings and the next round are what I have today. So a sub-martingale is a winning game and a super-martingale is a losing game. Okay? So a winning game means greater or equal and a losing game means less or equal. So remark, X is a sub-martingale if and only if minus X is a super-martingale. So in general, my statements, all my theorems will be either for sub-martingale or for super-martingale, depending how I feel at a given moment. But of course, you can pass from one another by just taking negative sign. And X is a martingale if and only if X is both a super-martingale and a sub-martingale. Another useful way to write this, of course, Xn is Fn measurable. Okay. So I can rewrite that condition, the martingale condition, as expectation of xn plus 1 minus xn given Fn is equal to 0 almost surely. Right, the x, by linearity, this is the difference of the two conditional expectations, and the conditional expectation of xn given Fn is just xn. So that's another way of saying this. I'm looking at the change in my process, and my current best prediction for the change is that it's 0. So example, let psi n be a sequence of independent random variables such that expectation, they're all in N1, in L1, and expectation of expectation of psi n is equal to 0. And I'm going to put xn is equal to, let me put x0 is equal to 0, xn is equal to sum of psi i's, I equal 1 to n. And so a simple symmetric random walk would be an example, but really I'm just asking for those to be independent and centered. Okay. So then such an x is a martingale. X is a martingale relative to the filtration Fn, which is generated by psi i's. We can think of these as, in the simplest case, these are flips of a coin. My filtration corresponds to the information about the first n flips, and my x is just the sum of the movements. So why is it a martingale? Well, psi I is by definition fi and hence fn measurable. Okay. All psi i's are in L1. L1 is a vector space, so their sum is also in L1. So xn is in L1. Okay. And the last condition, well, often with sums, the easiest condition to verify is this one. Okay, so I'm going to look at expectation of xn plus 1 minus xn given fn, but this is just expectation of psi n plus 1 given fn. And now what do I know about psi n plus 1? It's independent of all the previous psi's. So in particular, it's independent of this. So these are independent. So the conditional expectation is equal to expectation, and that's 0. Okay, so that shows me that x is a martingale. What else can we say straight away? Well, if I take n larger than m, and I look at, so suppose x is a martingale, and I look at expectation of xn given fm. Well, let me take a sub-martingale. And of course, everything else you can deduce. So of course I can, so here I have some gap, it's not n minus 1, but I can, by Tower property, okay, this is the same as expectation of, conditional expectation of xn given fn minus 1 given fm. That's Tower property. And now I know, because x was a submartingale, I know that this is greater or equal than xn minus 1. Okay. So this is greater or equal than expectation of xn minus 1 given fm. And I can continue this, of course, right? And so you can iterate, and you get greater or equal than expectation of xm given fm, which is just equal to xm. Okay, so this, I wrote this with one step, but of course you can really deduce from it straight away that you have this inequality for any previous moment in history. And maybe last very simple remark. If x is a submartingale and GNs are smaller than FNs, but such that x is still GN adapted. So if I have a smaller filtration to which I'm still adapted, then I will be always also a submartingale with respect to the GN. And so in particular, if you have a submartingale in a filtered probability space, you can always take the smallest filtration to which is adapted, which is its natural filtration, just generated by observation of my process, and my process will be a submartingale relative to that filtration. Okay, so x is an fx and submartingale. This is again just an application of the Tower property, right? Because if I look at expectation of xn plus 1 given Gn, then this is equal to, and I'm going to condition on a larger sigma algebra. So a conditional expectation of conditional expectation. And then because I knew xn was a sub-martingale with respect to fn, this is greater or equal to an expectation of xn given gn, but xn is gn measurable, so this is xn. So this is quite simple. The other way around, it doesn't work, right? If you have a sub-martingale relative to some filtration, and you take a larger filtration, clearly you'll still be adapted to the filtration, but you may very well lose your sub, super, or martingale property. In particular, if you give yourself knowledge of your future values of the process, well, then this will be just xn plus 1. Right? If in Fn I know, say, all future values of x, then this is trivial. This is just xn plus 1, etc., etc. Right? So making filtrations larger can be quite, can really change the nature of your processes. If you have well-behaved processes in this sort of sense of behavior, then making a filtration smaller, but keeping the enough information to keep track of your process doesn't change the nature of your process. And maybe another example. So I had one additive example. Let's have an multiplicative example. So let psi I be IID, and such that expectation of exponential of psi I is finite. Okay, so I take some random variables with exponential moment, and then x0 equals to 1, and nx equals to expectation of psi1 plus psi n divided by, let's call this c. C to n is an f psi n martingale. Okay, so this fn psi is the same one as here is generated by this random variables psi. So again, by definition, this is now this is a non-negative random variable, so the expectation is always well defined, and I see that this is in fact expectation of this is equal to c to power n. And already from here, but also from there, right, you can observe something. So if you take this observation, so we had greater or equal for a sub-martingale, but of course we had would have equality for martingale. Okay, so you can see that if x is a sub-martingale, then expectation, so taking expectation on both sides, I get expectation of conditional expectation is just expectation, so I have expectation of xn is greater or equal than expectation of xm. This was for sub-martingale, I would have equality for martingale. So in particular, martingale is constant in expectation, but that's a much weaker condition than requiring this equality here. But that's why you sort of would expect this normalization to happen, right? All right, so let's try to compute here. So this is multiplicative, so it's not very good to look at the differences. So I'm just going to look at the variable itself. What do I get? But here I see that xn plus 1 is equal to xn times exponential of psi n plus 1 divided by c. And now this is your most basic somehow application of the conditional expectation properties. This is measurable. So by this taking out what is known, you can pop it outside of conditional expectation. And this one is independent of this. So together you get that this is equal to xn times the regular expectation of e to psi plus 1 divided by c. And of course I've picked this in such a way that this is equal to 1. And I'm done. So we had two examples. Quite simple, but quite general because I didn't assume much about these random variables. I needed independence and center there, and here I just need, I took IID for simplicity, but of course, you know, I could have had different C's and just normalize this by the product of C's if I wanted to. So another example will have actually, I'll call it proposition. So here's how you can produce more martingales or sub-martingales if you already have some given to you. So suppose X is a martingale, of course on a given filtered probability space. And I'll take F, which is convex, and such that expectation of F of Xn is finite for all n's. I can put here absolute values, I don't have to. Of course, the expectation of F of Xn is bounded below by a linear function of Xn. So I know that this is, it has well-defined expectation, but it could be infinity. Then F of Xn is a submartingale. Go proof. F is a measurable function. Composition of two measurable functions is measurable. So F composed, well, F of Xn is Fn measurable since Xn is, right? So X was a submartingale, so it was in particular adapted. So I know that Xn is adapted. Measurable function of a measurable object is measurable. By assumption is in L1. So I really just have to check the defining property of submartingale. So I look at expectation of F of Xn plus 1 given Fn. And now I'm using conditional on Jensen to say that this conditional expectation is greater or equal than F of conditional expectation. And now, of course, by martingale, this is equal to F of Xn. And I'm done. And straight away, you can play around with this. You see that if I had X, so here I used that X was a martingale. If X was a submartingale, then I would know that this is greater or equal than Xn. So I would need F monotone to be able to write greater or equal here, for example. Okay, so you can take X, which is a submartingale, and F, which is increasing convex, will have the same statement. So I think there's more on the exercise sheet, but you can play around with this. So corollary, take your favorite convex function. So this is all subject to integrability. But if X is a martingale, then a litany of my favorite convex functions gives me submartingales. So absolute value of Xn is a good one. Xn squared is another one. Xn minus k positive part. Exponential of a function of a constant times Xn, etc. are all submartingales. So that's a useful way to produce submartingales, so more of our type of processes if you have one given to you. Now I want to introduce another way to do this, so another way to produce more martingales from given martingales. So maybe let's put a definition. A stochastic process, I'm going to use V, n greater than 1, is predictable. It's predictable if you can tell its value one step ahead. Okay? So if Vn is Fn minus 1, measurable for all n's greater or equal than 1. And then theorem or theorem, proposition, lemma, I mean, a very simple statement, but one which will be really very useful and will become a very powerful tool to prove statements which otherwise are not so easy to see. It really gives us sort of discrete stochastic integration. So suppose I'm going to start with a martingale, let's say Mn. And suppose Vn is predictable. I'm going to define Xn as sum of Vk times mk plus 1 minus mk. Let me put this k minus 1 in this way, because then I can start from 1 and go to n. I'm just going to put x0, 0. The interpretation of this, so those of you doing my finance course might have seen things like that. I also had an object like this in the very first lecture, if you remember. The interpretation is that one possible interpretation, it would be that, if this is somehow outcome of a stock price or some gambling or whatever, then at time k minus 1, you decide to buy these many shares. This costs you minus Vk times the current price. And then you hold this number of shares for one period of time. And then when you get to time k, you sell those shares and you get Vk times mk. So this is somehow, this one step here is outcome of your trading in one period. And the statement I'm going to make is that Xn is a martingale, subject to integrability, which somehow means that if this was a fair process, then whatever gambling strategy you can devise, you cannot cheat it and you still get a fair process. Then if Xn is in L1 for all n's, then X is a martingale. There's nothing difficult to prove here. Okay. I've assumed it's in L1. If I look at this definition, I see that this is Fk measurable, so it's in particular Fn measurable. This is Fk minus 1, so also Fn measurable. Difference of two Fn measurable things is Fn measurable. This is Fn measurable. So this whole thing is Fn measurable. Sum of Fn measurable things is Fn measurable. So Xn is Fn measurable, being a sum of products of Fn measurable things. So all I have to check is the defining property, but this is quite simple. If I look now at Xn plus 1 minus Xn given Fn, then this difference is just the one term in the sum. So I get expectation of Vn plus 1, Mn plus 1 minus Mn given Fn. And now I'm using that this is a predictable process, so Vn plus 1 is Fn measurable, so it pops out. And I get a 0 because Mn is a martingale. And again, you can improve this, well, you can prove variance of this result, right? If your process M was not a martingale, but a sub-martingale, then here you would get this is greater or equal than 0. Okay? So you need V to be non-negative and predictable for you to be able to write this is greater or equal than 0. Okay? So if you start with M, which is a sub-martingale, and V, which is non-negative predictable, then you get a sub-martingale. And likewise, you can play around with super martingale. That's also true, because if this is non-negative and this is less or equal than 0, then you get less or equal than 0. Some, again, of those variants are on the problem sheet. There's nothing difficult here. So we had a couple of examples of martingales. I didn't really give you any examples of sub-martingales or super-martingales. Maybe I can. But we had this way of building sub-martingales. We can have some trivial examples. Okay, so if x is adapted, integrable, and non-decreasing, then it is a sub-martingale. This is, of course, a much stronger property than I'm really increasing, but even a deterministic increasing process is a sub-martingale, and a deterministic decreasing process would be a super-martingale. But I want to come back to the first example there. If I take this example, and I work with this board, you won't see this example anymore, let me maybe leave it there and come to this board. This is continuation of the example which said I can apply my corollary to deduce that the process that I'm there is squared will be a sub-martingale. Okay, so subject to integrability. So maybe suppose expectation of psi I squared is finite. Okay. In fact, let sigma I be the variance of psi I, which is think psi as percenter, so it's the same as the second moment. So then we say that xn, which is sum of psi k equals 0 to n, is a martingale. So from here, I see that xn squared is a sub-martingale. And you can show, it's not difficult, okay, next exercise, that xn squared minus the sum of sigma i's squared is a martingale. Now, of course, this sum is the same as just the expectation of this, so this is still a centered process. Well, this is maybe a little bit surprising. I had a sub-martingale, something that goes up on average. Right? Martingale really is something that could go up and down, but whenever I am, I sort of expect it to be going up and down on average with equal probabilities. Not equal probabilities, but if it's going far up with a little probability and most of the probability goes down, but much closer, that's still okay. But on average, my increment is 0. The sub-martingale on average increases. But here I said that I can subtract actually a deterministic process from my sub-martingale to make it again into a martingale. And this is a phenomenon which happens in general. But of course, in general, you cannot expect this to be deterministic. This is deterministic because x is just the sum of independent random variables. But the following theorem is true. So this is Doob's decomposition theorem. So on a filter's probability space, let x be an integrable process. Again, an integrable process just means that each xn is in L1. Right? Then I claim that the following happens. Xn can be written as x0 plus mn plus an, where m is a martingale and an is predictable. Let me write this way. Is predictable. And because I've isolated the initial value of x, I can take m0 equals a0 equals 0. This is, of course, when I say martingale or predictable, this is all relative to the same given filtration, Fn, which was fixed. And this decomposition is unique. In the sense that if m a and m prime a prime are two such decompositions, then probability that they're equal, so mn is equal to mn prime and an is equal to an prime for all n's is 1. I can of course modify them on some null set, but in general, in this almost sure sense, they're strongly unique. And maybe third process. X that I started with is a sub-martingale. If and only if, well, for x to be a sub-martingale, it has to be increasing some Horn average. This is fair, so this means that this has to be increasing. So if and only if A is an increasing process, and of course, by taking minus, this is a super martingale, if and only if A is a decreasing process. Those of you doing continuous martingales will see a version of this result in continuous time. In continuous time, this is a really quite difficult thing to prove. And you'll probably not have a proof in the continuous martingales course, because it would take over a lecture, I guess. Maybe you'll have a sort of outline of the proof. In discrete time, we're quite lucky. It's reasonably straightforward to prove. Okay. So it can sort of first be somewhat surprising because I'm taking any integral process and say I can decompose it in this way. But in fact, the way you prove it is you just take this decomposition and use it as a definition of your process. Okay? So I can write this in a number of ways, but maybe let's start with my process A. Okay? So what is an? What's the increment of my process A? Well, A is supposed to be predictable. So if it's predictable, then this increment is the same as the conditional expectation of this increment given Fn, because both an and an plus 1 are Fn measurable. But now from the definition there, I see that the difference of ans is the same as the difference between xn plus 1 minus mn plus 1 minus xn minus mn. Okay, the x0 of course cancels out. Now, using linearity of conditional expectation, what do I get? I'll get expectation of xn plus 1 minus xn given fn, and then minus expectation of mn plus 1 minus mn given fn. Now that has to be 0. And so I see that the increment of a is equal to this. So this shows you, okay, it's somehow that if a process A exists, that works there, then it's defined uniquely from x. On the right-hand side now, I only have something that works from definition of x. But now, of course, I can use this as a telescoping sum to define n. Okay? So from here, I see that an can be defined. So a0 is 0, and then I get a sum of conditional expectations of xk plus 1 minus xk given fk. And now I just have to get case right. So a1, so this will be k0 to n. And I could, of course, rewrite this as sum of expectations of xk plus 1 given fk minus xk, because xk is fk measurable. So if you want, this is now my definition of an. That's a well-defined process. And I got, let me see if I got this should be na plus 1, right? All the way to na, this an plus 1. Okay? So in particular, each of this is fk measurable, and hence fn measurable. So my process is predictable. An plus 1 is fn measurable. Okay? And it defines a process, and of course it satisfies this, so we see that this is the process that matches things. What about m? How I'm going to define m? Well, again, this is not too difficult. I'm just going to use this definition. Okay? So one way to think about this is to think about the increment of m. Okay? So if I go from n to n plus 1, then m goes from n to n plus 1, and a goes from n to n plus 1. But the increment of a from an to n plus 1 is already known one step ahead. Okay? So the only thing that I can to compensate for the increment of x will be in mn. So this is somehow one way to define this. So mn has to be whatever is left from there. So I'm going to define mn as sum from k equals to, if I want to have this way, this will be xk plus 1 minus expectation of xk plus 1 given fk. And then k goes from 0 to n minus 1 now. Okay, if I want to be consistent, I will define it in this way. Okay. And so I'm looking just at, I'm summing the increments between x and its prediction. So this is a definition. Okay. Clearly, each of these elements is fk plus 1 measurable, because that's fk plus 1 measurable, that's fk. So this whole thing is fn measurable, as fn plus 1 measurable. X was in L1, so both this and this is L1. Sum of L1 random variables is in L1. So L1 being a vector space, I get that my process M, so defined, is in L1. And now I'm just going to check the Martingale property, so I'm going to look at expectation, conditional expectation of Mn plus 1 minus Mn given Fn. That's the martingale difference for my process M, but this is just the last term here. So this is the same as expectation of xn plus 1 minus the conditional expectation of xn plus 1 given fn, conditionally on fn. So now by linearity, this is the difference of two conditional expectations. But here, of course, I already have something that's fn measurable, so having this additional conditional expectation doesn't change anything. So this is just conditional expectation of xn plus 1 given fn, which is equal to this, and so I get 0. Another way, if you wanted to think about this, is that once I've observed that process A is uniquely defined by its property of being predictable there, of course, process M is uniquely defined by this equality there. Okay. So this gives you both existence and uniqueness. And lastly, what does it mean for X to be a sub-martingale? Well, it means that all of these conditional expectations are non-negative, but then the process A is increasing. Okay. And of course, the sub-martingale is, super-martingale is if these are non-positive, and so A is decreasing. So I can apply this to that example there, if you want, more generally, okay? So I can take this example here, and I can say that if X is a martingale in L2, so square integrable, then there exists a predictable process. And instead of A, I'm going to denote this angle bracket of M, of X. Let me use M for my martingale. Such that Mn squared minus this angle bracket is a martingale. We're not going to come back to this process. We don't use it so much in discrete time, but you will see that this also carries over to the continuous time setup, and this process will be essential. It will be essentially your clock of what happens to your martingale in continuous time. And while I'm at this, of course, maybe another very simple remark from this definition would be that the set of martingales is in fact a vector space, so I can take linear combinations of martingales and I still have a martingale. Okay, so martingales for a given filtration. So maybe let me write this like this. F and martingales form a vector space. And of course, a constant process is a martingale. And what you can see clearly is that if X is a martingale, then the process xn minus x0 is a martingale, because I subtracted something that's integrable and f0 measurable, so measure with respect to all fn's. And this process starts in 0. So quite often, without loss of generality, you can assume your martingale starts in 0. That's sometimes useful. And by default, all these processes in my Doob decomposition, they start in 0. And I will often want this to also start in 0. Do you have any questions? There's one more example that we need. what I would like to have. Okay. So let's take x, an L1 random variable. Okay. Then I claim that xn, which is defined as the conditional expectation of x given fn, is a martingale. Now, this is just tower property. This is in L1 because conditional expectation of integrable random variable is integrable. Adapted by the first property of our conditional expectation, this is fn measurable. And then if I look at conditional expectation of xn plus 1 given fn, then this is conditional expectation of the conditional expectation of x given fn plus 1 given fn. And so the tower property, this is larger than that, tells me that this is simply the conditional expectation of x given fn, which was the way I defined xn. So I have the martingale property. And this is a very important way to construct martingales. Okay. What are we doing here? We have some sort of target. And as we acquire more and more information, we build more and more precise approximations or projections or our best predictions of that target. Now, if there is some justice in the world, then you would be inclined to take limits in this expression, right? So we have f infinity, we defined that. So if x is, say, f infinity measurable, then I would like to understand that this somehow should converge to x infinity, and this should be equal to x. What I don't know, well, I don't know if there's really enough justice in the world for this to happen, but hoping that there is, then at least, I have to make sense of these arrows. It's not clear, what sense those arrows hold. And to make sense of this, we will need to go back to the notion that we've skipped, which is the notion of uniform integrability, which is the notion that really characterizes when I can go back from convergence in probability to convergence in L1. Okay, so we had dominating convergence theorem, which allows you to, say, go from almost true convergence to convergence in L1. That was sort of a sufficient statement. But we've skipped this uniform integrability, which is a finer notion, which gives me if and only if. And next week, we'll start by doing some more technical work on this notion, because this will be precisely the notion that we'll need to then study convergence of martingales, and in particular, to understand that example, which somehow is our motivating example. Okay? I'll see you next week. Thank you.